Alright guys, so here we go. I'm going to do my best to introduce you today to the idea of limits. We're going to do a whole bunch of different things with limits, but we're going to do our best to kind of get an idea of what these are. Now these are essential to the idea of calculus. They're essential to the idea of derivatives. They're essential to the idea of integrals. And this is going to be the start of it all. Okay, now this is what a limit looks like. My assumption is that you know nothing about limits. So here we go. We got a limit. As x approaches a, which is some number of a function, and that's going to be equal to some other number here. All right, now the idea of a limit is we're going to say as x gets closer and closer to some number, now it can get closer from the left or from the right, but as x gets closer and closer to this number, what happens to f of x? What does the value of f of x become? That's what a limit is, just in simple terms. All right, now I'm going to go through a couple of examples here, and then we'll look at some specific details and some things that'll be helpful as we really start to look at limits. All right, so the first one I'm going to look at is going to be rather straightforward. We're going to say the limit as x approaches 2 of x squared. All right, now you can already probably figure out what the limit as x approaches 2 of x squared is. What happens as x gets closer and closer to 2? Well, you should be able to figure out that it's going to give you an answer of 4. But what I want to do is I want to show you here on the calculator so that we have a better idea of what's going on. So I'm going to go y equals x squared, and we're going to look at the table. Okay? So as I get closer and closer to 2, I'm going from 1 to 0 to 1 to 4. And then from this side, I'm getting a little bit smaller. But that's not really the detail I want. I want to get a little bit closer. So I'm going to actually go here, and we're going to change the table to go by tenths. All right, and this is going to be a little bit more clear. We want to see both the below the 2 and above the 2. This is from the left, getting closer to 2 on the number line. This is from the right. Okay, so as I look at that, I see 2.89, 3.24, 3.61. They're getting closer to 4, right? 5.29, 4.8. Still not quite as clear as I'd like. So we're going to go ahead and we're going to make it even closer. So we're going to go 0.01. All right, so what happens as I get closer to 2? Again, you can see 3.8. Look at those numbers. They're getting closer and closer to 4 on both ends, both the right and the left. All right, and if I go one more, let's go 0.0001, just it's going to make some even finer steps, and you can see how those numbers, it's very, very obvious just by looking at the numbers that you're getting closer and closer to 4 from both sides. All right, now in some cases you can just take that number and put it in, and you can find out what the limit is. All right, now in some situations that's not really possible. For example, if I had the limit as x approaches 0 of 5x plus x squared over x. Now this one obviously isn't possible to do just by putting the 0 in, because I'm going to get a 0 on the bottom. So the question then is, okay, well, as x gets close to 0, what's going to happen? All right, well, let's first look at the calculator. We'll go back into our y equals. So we're going to go back into 5x plus x squared. All right. And 5x plus x squared, and then divide it by x. And we'll go into our table. It didn't like that, did it? Oh, sorry about that. Let's just get rid of this. Alright, now we go into our table. And this time I'm doing as x approaches 0. So, oops, let's go back to 2. We'll go back to our value of 1. So as we get closer and closer to 0, I got 11, 10, 9, 8, 7, 6, error. Okay, now looking at the numbers below 0, I got 1, 2, 3, 4. Can you guess what it's getting closer and closer to? Well, you probably can, but you know what? Let's change our table a little bit. We're going to go ahead and make a jump. We're just going to go straight up to 0.01. What happens if I look at hundredths? Well, look what happens. as I'm approaching from below 0, I got 96, 4.97, 99. Looks like we're getting closer and closer to the same number, right? You could get smaller and smaller increments, but I think the idea is clear. We're getting closer and closer to 5. Now, what that means is that it's converging. All right, that means that as we go from the left and as we go from the right of x on a number line, we're getting closer and closer to 5. Now, at x equals 0, it doesn't actually exist. And we've talked about this before. That means that there's some kind of hole there, right? But that's why there's a hole. That's the removable discontinuity, just because at 0 it doesn't exist, but on both sides it's approaching the same number, and we can see that here. Both sides it's approaching that 5. Okay, now we talked about before how we could kind of deal with that. We're gonna learn some more ideas about how to do this. Shortcut is just to kind of say, okay, well, let's factor out the x, which will make it 5 plus x over x. We then cancel out the x's, which technically is not okay, but because we're saying that x is not equal to 0, x is approaching 0, that means x isn't quite 0 yet, it's just getting really close, then the x's can cancel out, leave me with 5 plus x, and then I can say, well, then as x approaches 0, this is getting closer and closer to 0, therefore my final answer will be 5. And so that idea can kind of help us. Now we're going to be looking at this. We're going to get some more details, but let me just finish with this for this video, and I'll do a couple more examples here, and then we'll lead into something else. Okay, this brings up the idea of continuity. Okay, so we want to be able to talk about whether functions are continuous. All right, now if something is continuous, then it has to follow these 3 rules. Number 1, the function is defined at c. So a function is continuous at c, sorry. At x equals c if the function is defined at c, which means that there's a value there. All right, number 2, the limit of f at c exists, which means I can do what I just did. Okay, I can find the limit. And number 3, the limit of f at c is equal to the value of f at c. Okay, now we've talked about discontinuities before. We've talked about asymptotes. We've talked about the removable discontinuities, the holes. And this is actually what makes something a discontinuity or makes it not continuous. Okay, if any of these are violated, then we say it's not continuous. So for this function right here, 5x plus x squared over x, it's not continuous because it's not defined at 0. Okay, the limit does exist, but it's not defined there. All right, so we'll go ahead and use that idea, and let me just do one example with this. Actually, let's do 2 examples, and then I'll pause, and you can go on to a different video. All right, so the first example we're going to do is this. All right, so here's our first example. We've got f of x, which is a piecewise function. It's changing as it goes. We're going to go ahead and sketch this first. Let's get an idea of what this looks like. Okay, so here we go. We're going to need our graph. And the first thing that I notice is that the values are all pretty small, so I'm not going to worry too much about it. It says if x is less than or equal to -1, the value is 1. So all the way up to here, up to -1, up to -1, the value is 1. So I got a straight line here. Okay, between -1 and 0, not including, then I have -x. So that means it goes like this, just like that, to 0. At x equals 0, the value is 1. Oops, sorry. There we go. Value of x is 1. And then negative x, again, from 0 to 1. So that means I've got kind of a little hole here. And then from 0 to 1, it goes down again. Okay. And then it's positive 1 again. So this is a hole. And then it's positive 1 from here on. All right, now our job is to then find the limits as x approaches -1, 0, and 1, and then to determine if f is continuous at those values. All right, so let's give it a try. Actually, I don't need my calculator. So why don't you pause it and then work through it yourself and see if you can answer these questions based off of the definitions that we've given above. And then I'll go ahead and work through it, all right? Pause it now. All right, now I'm going to assume that you've gone through this by yourself, but let's go ahead and talk through it. So we're going to find the limits as x approaches -1. So limit as x approaches -1 of f. So as it approaches -1, as we go from the right-hand side, note that the value is always 1. 1, 1, 1, 1, 1. So we're approaching 1. All right. If we approach from the left-hand side, note that it is lower than 1 here, but as I go to the left, as I get closer and closer to -1, the value of the function is getting closer and closer to 1. So therefore, it does approach 1. All right. Let's look at the limit as x approaches 0. All right. So as x approaches 0 from the left, I'm getting smaller and smaller and smaller, closer and closer to 0. As it approaches from the right, I get closer and closer and closer to 0. So the limit as x approaches 0 is f equals 0. Note that at 0, the value is 1, but that is not what the limit is. The limit is describing what happens as I get closer and closer and closer from opposite sides. As I converge on that point, what is the limit? What does it get closer and closer to? All right? So then we're going to look at the last one. So the limit as x approaches 1 of f. Now note that as I approach 1 from this side, I'm getting closer and closer and closer to -1. I'm getting more and more negative. Now as I approach 1 from the right, I'm at +1, +1, +1, +1. So I'm approaching two different values. And the way that I could write this is the limit as x approaches 1 from the left, so that little negative sign means from the left, of f equals -1, but the limit as x approaches 1 from the right is equal to +1. All right, now because the limit is different on both sides, then we say that the limit as x approaches 1 of f is undefined. Okay, and so we just define it as undefined. Now, for letter C, it says determine if f is continuous. All right, well, obviously for this one, as x approaches 1, it's not continuous because it doesn't even have a limit there. It does have to have a limit. The limit has to exist. That was rule number 2. All right, the next question, the next one we would look at, we could look at either of these. If we look at limit as x approaches 0, we got 0, but what is the value at 0? If x equals 0, f is equal to 1. So that then violates number 3. The limit of f at c is equal to the value of f at c. I have different values, which means that it is not continuous at that point. All right, the last question then is the first one continuous? And because the value, the limit of f as x approaches -1 equals 1, and the value at x equals -1, I get a value of 1. 1. So because those two are the same, that then means that it's continuous. All right? Now, of course, we can't leave it at that. That was way too simple. So let's just add in one more question, one more example. Let's now consider something a little bit different. F of x equals x cubed minus 3x squared. Yeah, I just did it. we just put in a polynomial, and it's going to be awesome. And then k when x equals 1. Alright, so f of x equals this function when x is not 1, and k when x equals 1. The question is, what value does k need? K equals what number so that f is continuous? Alright, now that should be fairly straightforward. It shouldn't be too difficult. We've got a function here. Obviously, putting 1 straight in is gonna actually is not going to be a problem at all, because I can put 1 straight in there. So what I'm going to do is just put 1 in. There's nothing wrong with that. If this was x minus 1, I might have to divide and cancel out, kind of like I did up here. But due to the fact that I can put 1 straight in, then I can actually find out what this is going to be as I get closer and closer to 1. So I'm just going to go to that. I'm going to go 1 cubed minus 3 times 1 squared plus 4 all over 1 plus 1. So I'm going to have 1 minus 3 plus 4 over 2. 1 minus 2 is negative 2 plus 4 is 2. So 2 over 2 equals 1. So therefore the limit, this now gives me the limit as x approaches 1 for f of x equals 1. Now because it's equal to 1, that's what I want k to be equal to. If k is equal to 1 at that point, that will then follow rule 3, where the limit of f at c is equal to the value of f at c. And so that would then make it so that this would be a continuous function. Alright, so now we've introduced you a little bit to the idea of limits, the basic idea. We've introduced you to the basic idea of continuity. And in the next video, we're going to really dig into limits and how we can deal with some limits, and limits with more complex things, and some more formal ways of dealing with it. Alright, so go ahead and finish this video and go on to the next.